and good afternoon, everyone. As Professor Argo said, in the SWAV group, we work with a lot of different folks. Oh, thank you. In the SWAV group, we do a lot of work on a lot of different aircraft, but particularly the talk I'm going to give today really touches on two of what I think to be some of the most integral issues facing urban air mobility, or the realization of urban air mobility today. So in thinking of how to give this talk today, I thought, okay, how can I make sure that the audience, I cater to both a technical audience as well as the younger audience. And for that, I brought two props. One actually is a prop. The second is, these are two lithium-ion batteries that are inside of a Tesla Model S, right? So my talk really today talks about how we can model these battery cells at a fidelity that is essentially suitable enough for conceptual design. So with that being said, before I get started, I want to first go over some key terminology that I'll be using today. The first one is RUAM, which stands for Rural and Urban Air Mobility. I think everyone knows the second, eVTOL or eVTOL, for conventional and vertical takeoff and landing aircraft. The third is the TAPOOL diagram. And this is one of the most significant contributions of my research, where essentially I'm trying to capture the performance of electric aircraft over a range of operations. So not just looking at the simplified brigade range equation or the electric version of that, but really, how do we incorporate time as an axis into those analyses? The fourth is sound pressure level, SPL. And then the last but not least is medium fidelity. And when I talk about medium fidelity, I'm talking about how can we introduce these models to really understand some of the physical nuances and some of the phenomena, but do it in a fast and accurate methodology to really promote iterative design. I'll just use my hands. So with that being said, we first need to start off with the applications of RUAM, right? And a study by Booz and Hamilton suggested these three. The first is last mile delivery. So this, you're thinking about the FedEx, the UPS. The second being air shuttles. So operating a regularized route and schedules, such as such as trains and metros. And then the last one being ride sharing, which really involves air taxis operating more personalized routes. But I'll stop here to mention the fact that your very own Professor Argo recently published a paper working with some colleagues in the National Academies where they talked about the fact that the actual initial adopters will actually be cargo, right? Delivery, full-scale autonomous delivery, where due to the fact that the adoption of transportation systems as well as perception has to be addressed, right? So looking at non-passenger traveling vehicles. So where are we right now? Well, this number is a little bit misleading, but there's actually, if you go on eVTOLnews.com right now, there's about 150 proposed concepts out there. But the problem is that there are no real significant consensus as to what configurations maximizes things such as efficiency, reliability, safety, right? These are the main issues. And to zone in on two of them, the first one is that a lot of folks in our field right now are modeling batteries that are in a pretty trivial way. And as a result, they're not able to capture some of the nuances. So I talk about electrochemical cell performance here, and I'm really also including things such as hydrogen. Professors in Texas, UT Austin are working on some very interesting hydrogen stuff here. But there's not really an accurate assessment of these types of cells. And lastly, the prediction methods of noise have fallen on two extremes. On one side, you have the very computationally expensive models, which can take hours and days to run. And the latter, you have empirical models that have been designed, have been used by the FAA, SAE, as well as some other agencies that can't capture some of the nuances that these new aircraft are going to experience. So that brings me to my research talk, which really seeks to, the five main questions are here. The first one is, during the aircraft conceptual design phase, and the keyword is of non-conventional aircraft, what design critical nuances can be unearthed, right? What are the things that we can find by modeling these aircraft at such a fidelity? The second is, what impact does repeated cycling of the battery itself has on the, over time, has on the performance of the electric aircraft? The third, and this is very important, especially as engineers trying to communicate to a larger audience, what are the new performance metrics that can be devised for folks such as the flight operations, market modelers? Number four, what regions of the flight envelope can we get away with a simpler methods such as frequency domain methods for acoustic prediction? And last but not least, which is very important for systems engineers, can all of these associations be quantified, right? How can you quantify, for example, if you reduce the noise on the aircraft by 10%, what does that mean for the energy of the aircraft over the entire period of the flight profile? So this talk is divided into three main areas. The first, I'll talk about electrification in the aerospace industry and where we are right now. And with that, I'll talk about lithium-ion battery modeling. The second half, I'm going to the second area of my research, which focuses on noise. And I'm using medium fidelity prediction noise methods, looking at rotor blade optimization. And then I'm going to study some test cases. And as you can see, there's some work here that's been published in the Journal of Aircraft. One has already been published, one is currently under review, and I just submitted some responses for that. And then the last one, I'm actually currently working on the manuscript right now. So this is ongoing work. So let's first dive into electric aircraft. And where are we? Well, I think this audience already knows that it's not a question about when, about if, but when will electric aircraft be integrated into our society? And NASA here summarizes, in this table summarizes the advantages. I mean, there are several, but in terms of the system level, you can see here that distributed electric propulsion obviously outweighs internal combustion engine. And then in terms of the operating cost, it's about a fifth. But notice here that there's still greenhouse gases produced by electric aircraft. Why? Some people may ask. Well, we still have to consider the fact that the energy needs to be created somewhere, right? At the grid level. So this is where that 9%, that 10 to 24 kilograms of CO2 comes from. And to address some of these issues, NASA has developed the X-57 Maxwell aircraft. And this aircraft is NASA's first aircraft in over 20 years, experimental aircraft, and it's meant to really service some of the certification, to really answer some of the certification issues that they're having right now. And here's a model of the battery. And within that battery, within this battery pack, you see their individual modules in purple. And within those modules are these guys, right? These are what is in those packs. But there are several different issues that have been occurring recently. I think if any of you have attended the recent SciTech conference, one of the talks was about the fact that there's a lot of fires in that they're experiencing with this battery module. So this just goes to show that this is a very, very relevant issue that they're having in terms of not only modeling, but also certification. So with that being said, I think the most practical thing to do is to step through what is really a battery, right? Within these particular cells, these are essentially just jelly rolled structures made out of 5 key components, right? And this is what I have here. You have the 2 current collectors on each side. Then you have a rock salt cathode, which is the lithium part. The anode is typically graphite. And then you have the movement of electrons across an electrolyte, which is typically an organic solvent. So when a battery is being discharging, as ions move throughout the cell, the electrical circuit outside is where we actually connect the load. And that's what we're feeling, or that's what we experience when we talk about the battery being discharging and charging and recharging. However, like I mentioned before in the aerospace industry, if you go to the Journal of Aircraft or some other studies, there's not really a lot of emphasis as to how the battery degrades over time. It's a stored energy cell, right? So therefore, there's going to be some changes in performance. And these can be summarized by repeated cycling, right? This repeated cycling typically causes thermal stresses, mechanical stresses, and it also forms this amorphous layer called the solid electrolyte interface, right? And this essentially just stops lithium ions from being deposited on the anode, right? And some areas on the cathode. In addition to that, you can think of when we consider, you will hear a lot of battery manufacturers say, you don't discharge a battery over exceed discharging the battery. But what does that really mean? Well, when you're discharging, you're essentially moving these ions to the other side of the battery. Over discharging means that you're ripping the last set of ions on the layers over to move to the other side, but this causes exfoliation, right? What does exfoliation does? It increases the sizes of the van der Waals gaps. And these van der Waals gaps, as they increase in size, you decrease the potential to hold more charge. And that is what it means by a battery losing charge, right? I think that really summarizes what it means. So with that being said, the key objectives in the aerospace world, we need to first outline the implementation of not only a discharging model, but an aging model. Then can we predict the performance of the aircraft over time? And then lastly, most importantly for the systems level, so this is where the FAA comes in, how can we identify the sensitivities of rates of climb, right? Of performance, of temperature on the performance of the state of health of the battery. So this approach is summarized into 3 parts. So now we have a motive. Let's go into to dive in a little more technical about how we go about doing this. So for the electrical discharge model, we're using a simple 7-in circuit model. So this is an empirical-based model where you first start off with the experimentation to collect data, then you fit the data, and once you fit the data, you use a set of ODE equations to characterize the discharge of the battery. And what this allows us to do is to capture some of the load modulation felt when an eVTOL is transitioning. Those are very important phases of flight that can't be modeled with a simple V equals IR, right? Secondly, we have the thermal model, and the temperature and heat generation is typically captured through conservation of mass and energy, right? And here the thermodynamic changes, like I mentioned here, are captured through numerical expressions. The first one is joule heating and entropy heating. So how do we start? Well, start off with a battery. This is the same module that you saw before. This module can be expressed in a diagram here where you have the SL, which is the longitudinal distance, ST is the transverse distance, and then V infinity is the flow going through the battery. What is this flow? Well, it can be air, it can be a fluid. It's just a cooling flow. So for aircraft, when we talk about air cooling batteries during flight, we're talking about how in flight, what's the temperature of the air going through the cells. And this is very important because I'll mention this in the future slides. Anyway, let's move on. So we have the heat generation model, and then we have the heat removal model, like I mentioned, from the flow. We have here this term here, Q convect equals to the total number of cells times that average heat transfer coefficient. So we seem to know everything in this equation besides this H, right? We seem to know, we need to figure out what is this H value here. So let's pay a little bit more attention to that. Well, this value is essentially a function of the Nusselt number, the Prandtl number, and a few other numbers. I won't bore you with the details, but essentially, once you have this H value, you can compute the log mean temperature difference, and then therefore you can compute the amount of thermal energy within the battery pack, right? So now we're moving away from these simple models to now predicting the temperature of our battery pack. And last but not least, we have a degradation model. Now, battery cells degrade in 2 ways. First is calendar aging. So if I set this battery down here, I'm sure some of you know this already if you have old toys or apparatus. If it come back in a year's time, this battery is going to degrade in energy, right? So that's what calendar aging is. And then cyclic aging or cycle aging is just the fact that as the cells continue to cycle, the energy is going to fade. So, you can think about combining the two. You have the capacity fade model, which is the fade of the battery energy, and then the resistance growth model, right? Which is talking about the growth of the SEI layer and some other elements within the battery that cause the resistance to increase. Well, you can imagine, what is resistance linked to? Temperature, right? So that's how you can imagine that the fact that as the battery ages, the temperature of the cell is going to change as well. So we have a model. So we have a purpose. We have a model. Let's actually apply it to flight profiles. So here I have 4 major metropolitan areas. They aren't all cities. Dallas-Fort Worth is what we call a polycentric location, which means that it's middle of 2 large cities. But here are essentially the routes you see in yellow are the routes I have here in this table, and then the dotted lines are just potential routes. So this graph these plots just show you the fact that within cities, we have to model these particular ranges and model them a lot, model them over a year, 5 years, to see what is the utility of these models applied to realistic flight profiles. Secondly, we need aircraft. Now, for this talk, I chose 4 aircraft. First is a conventional twin-engine aircraft. The next 3 are 3 aircraft that symbolize the 3 main categories of eVTOLs. You have stopped-rotor vehicles, tandem tilt-wing vehicles, which are essentially vectored thrust vehicles, and then lastly, you have hexacopter aircraft. And then in addition to that, we have each aircraft is modeled over 1 period of year, 8 daily flights per year, and we only recharge at 1C because they're only looking at the flight profile, effects of flight profile. And as you can see, for the particular aircraft, they're modeled using the realistic segments. So for our conventional aircraft, you have a takeoff and landing. We have these 2 segments, which really are certification, are essentially based on certification standards but set by the FAA, as well as you have a landing and reverse thrust. Compare that to, let's say, a tilt-wing aircraft where you have a vertical climb, a few different transitions, and then a vertical descent. But you can think about, and I think Professor Argo and Professor Frew and some other people know in this talk, you can imagine how much data you get from 1 flight. Imagine 8 flights per day over an entire year. There's an issue of there's so much data. And that's the reason I came with this particular diagram called the TAPOOL diagram. And this diagram essentially describes the behavior of an electric aircraft over its entire life cycle. And it differs from traditional methods, which are typically the electrified brigade range equation, in 2 ways. The first way is that time dependency is introduced into the efficiency of the storage energy system. And secondly is that we use the entire flight profile. The standard brigade range equation only looks at a particular flight condition, range, velocity, etc. Now, this is where things get pretty interesting, right? And I'll start off with this first plot and explain it, and then you can take the trends throughout the entire for the other aircraft. But what we expect to happen, for example, if you're flying a flight profile of 100 nautical miles, this aircraft can only sustain it for about 80 days until it cannot sustain that flight anymore, right? Compare that with a flight of 70 nautical miles, which essentially states that this aircraft can fly about 300 days before that aircraft cannot sustain that 70 nautical mile flight. That's one of the takeaways from this plot. The next, and I think which is the most important takeaway, is the fact that this plot really tells you about utility. Essentially, if you're flying from New York to Philadelphia, that flight is about 100 nautical miles. What this plot is saying is that you can actually repurpose that aircraft to a flight of 70 nautical miles and fly between JFK and New York, right? And the reason why this is important is because for battery-powered aircraft, there's a lot of talk about how we should go about utilizing these aircraft. Should we swap out the battery after each cycle, or should we recharge? The problem with swapping batteries is that every time you take out and put in a battery, you're weakening the electrical, you're weakening the structural integrity of the ports connecting the two. So you really don't want to be taking in and out the battery all the time. So what these plots actually convey is how can you actually maximize the utility of an electric aircraft, taking into consideration the fact that the energy is going to be decreased over this entire flight profile. The second one, which I mentioned to you before, so the second diagram, the temperature to pool diagram. And I'm going to go to this last plot here because I think this one pretty much summarizes it. Can anyone guess why the battery temperature is a little bit high in this area? And this wouldn't be captured in any of these simple methods. Well, in San Francisco, this period, day 250, between day 200 and day 300, is very hot in San Francisco, right? So these plots actually can tell you that even flying at a particular range, there's some periods of the year where the battery is going to be experience higher temperatures. And why is this important is because it goes back to the question of safety and certification. We need to have an idea of how the temperature within the battery changes, because that's important for battery management systems, thermal management systems, because these are, if you design the aircraft to remove a certain amount of energy, let's say in January, the battery is essentially going to explode in July, right? Those are the critical things that we need to start to think about in this research. So to end off this first half of this presentation, the future direction, obviously involves the improvement of the models I'm using, as well as experimental testing, but also looking at cell inverse design. Once you have an idea of how the battery is going to perform, can you create a battery that can do that before using off-the-shelf batteries? And then, talking about thermal management is very important. And lastly, and this is very important for flight operations, as I guess work that Zach does as well. How do you maximize the utility, right? How do you maximize the utility of these aircraft? So I'll stop here for a split second before I go into the next half of my talk. Are there any questions? Yep.
So looking at the sort of flight profile, versus time range, how did you factor in the, I'm going to say the energy demand, the elements of the flight path have different relative demand, right? So
yes.
Time versus cruise.
Yes.
And so when you actually factor in that fractioning, I would have expected to see much more nonlinearity than actually.
Yeah. Yeah. So that's a good question. Those, when you model this aircraft over a period of time, essentially I'm looking at the holistic picture. But if you ask, like actually in some of the additional slides at the end, I actually show you which flight profiles cause the aircraft to degrade more, right? So those do factor into the particular, for one individual flight. However, if you're looking over an entire lifetime, I decided to systematically ignore them because I'm looking at the bigger picture. But they do play an important role. And I talk about it in my thesis, the fact that you have to also look at the flight profile itself, because that actually can be modified to reduce the amount of energy you're using.
Well, and I would even think that 70-mile flight may actually not be as good. If you're not careful,
exactly.
It actually is worse because you have more climbs and takeoffs and landings than you do cruise. It's like cruise miles versus climb miles.
It also depends on the aircraft, right? Some aircraft are more efficient for hovering and vertical takeoff versus, so there's a cost benefit of the range versus the type of flight profile and the type of aircraft it is. Yeah. Yep. Yeah, so the battery, I kind of glossed over it, but the battery models actually consider not only the energy used, but things such as the C rate and temperature, right? Those actually cause the degradation of the cell. Those cause certain other nonlinearities in terms of the discharge profiles. So those are taken into consideration in these models as well. Okay. Yes, one assumption is that there's I'm using ideal batteries. So one of the things you're going to know is that when you design a battery pack, not all cells are ideal. So there is work here to be done in terms of quantifying that uncertainty. Yeah. It does capture. It's only between, I think, 97 and 99% of cells in that range. They're all in terms of like the rated capacity. Cells only range between 97 to 99%. They're very well quality controlled. Tesla, I think, creates an absurd amount of these per second. I think 500 or so. I'm not really sure. Yeah, so they're very well monitored. Okay, so I'll move on to the second half of my presentation. It really focuses this picture here actually does a good job in summarizing the second half of this presentation. The fact that community noise is going to be an integral factor for vertiport placement, right? And the acoustic footprint of these aircraft are going to really dictate the approach and departure corridors that are going to have to be created. However, the problem is that the current noise prediction methods aren't really suitable for this iterative design. So we need to address this in some way. Modeling acoustics typically comes in the form of this equation. This is a governing equation by Goldstein. And to model the equation to capture the pressure distribution and fluctuations, it's typically done in two ways. The first way is a frequency domain method, where you use a series of Fourier transforms, Bessel functions to convert this equation from x of t to x of omega, which is in the frequency domain. And then the second method is to essentially discretize this equation as is this formulation 1A that Penn State uses. There are other different formulations into the time domain, right? And this is where you get the Fox-Rayleigh-Hawkins equations discretized and you can compute the sound. However, as you can see here, the frequency domain methods are less computationally expensive than the time domain methods. So for this talk, I'll be focusing on the frequency domain methods. Now, in terms of the noise produced by these aircraft, well, this aircraft produces several different types of noise, but this diagram here really summarizes the main contributions. You have contributions based on that are the function of the rotational frequency. So you have thickness and loading noise. You also have broadband noise, which comes about due to the fact that there's going to be a lot of turbulence, blades impinging on wakes, etc. And then lastly, interaction and distortion effects. And this image here actually does a good job in capturing the types of noise and where they're produced. So at the lower frequency, you hear the wop, wop, wop sound that we hear from the helicopters. These are these spikes here. And then that humming sound you hear when helicopters pass at the high frequency, that's the broadband component of noise. So that's the characteristic noise signature of aircraft. And modeling these components now, for the harmonic noise, we have the loading component and the thickness component. These are very long equations, so I'll just focus on the key elements of it here. We have theta r, which is essentially a function of the radiated noise of an aircraft moving in the air. As you can imagine, when an aircraft creates a sound, by the time the sound gets to the observer, the aircraft has already moved forward. So you really want to capture that angle. For the loading noise, we have the differential thrust and differential torque. Kx here is just the wave number of the sound. Phi of S captured the fact that for blades that are swept, you can actually dephase the noise to increase the energy in the spectrum. And then lastly, Jm is just the Bessel function of the first order that comes about, like I mentioned, when you convert that first equation to the frequency domain. On the second half, looking at broadband noise, like I mentioned before, it's really a contribution of several different noise sources. And this plot by Leishman, really actually by Brooks, gives you an indication of what are the different components of broadband noise here. In this study, I'm only modeling this blue line, the turbulent trailing edge noise, because I argue that for aircraft flying in cruise condition, these two, the green and the orange, are not as significant contributors. They will be obviously for transition phases where you have a lot of wakes interacting. However, you can get away with only the blue line for conceptual design in certain cases. And then for that, I'm using Amiot's model, which essentially captures using the properties of the boundary layer of the airfoil. You can capture essentially the pressure spectrum radiated by one blade section. Then you can integrate that over the entire blade, about the number of blades, and then you can get the total sound pressure radiated over the entire, the total broadband component over the entire aircraft. Now we have the components. Let's look at some validation cases. The first validation case, I'm going to talk about the strength of the harmonics, and the second case is the directivity. So looking at the strength, we have good agreement with the experimental data and A0 pass, which is a tool developed at NASA Langley. For most of the conditions, to how to read this plot, essentially each column is just a different test case. These are different thrust coefficients. And then each row is just the angle of the microphone measuring the sound. So you have 60-degree microphones on the first row, and then on the second row, you have your 90-degree microphones. So we see there's pretty good agreement within the harmonic prediction of noise. What about the directivity? You know, if you have microphones positioned around the rotor, how does it look? Well, we see there's pretty good agreement between 30 to 60 to 160 degrees. However, the prediction breaks down essentially in front and behind the rotor. And I'll talk about a little bit in the future, I'll talk about why we're still able to get away with this, even though the prediction is not as strong in that area. So that's the harmonic noise. And then for the broadband component, doing a little validation, I'm using Zawodny's work at NASA Langley in the SALT facility, where essentially he modeled, in this facility, they extracted the narrowband spectrum from a APC blade. And then what he did was that he converted it to the 1/3 octave spectrum and isolated the broadband component. So I'm going to look at that broadband component now and compare that with the data. Although there's a general trend in our results compared to experimental data, we see there are still some non-linearities and still some differences. This can be put down due to the fact that I'm only modeling one of the several components of broadband noise. Also, we believe that some of the extraction of the broadband from that narrowband spectrum wasn't done well in certain areas. So there's a lot of still work to be done in terms of matching the experimental and the prediction data. But overall, there's still a pretty good agreement in terms of the entire sound pressure spectrum. We're able to capture the harmonics like I mentioned before at the lower spectrum. And then we're able to capture just the general trends for the broadband, the higher spectrum. But that's all fine and good, but how does that compare with CFD? Well, here are the results comparing a case that was done at, I think, Virginia Tech for two different, well, one was the Virginia Tech and one was another study by Tan in 2014. But essentially, in this plot here, it shows you that we're able to capture the first two harmonics, but we're doing a pretty poor job in capturing the harmonics. So there's still some work need to be done in comparing this, in really improving this model that we're using. And then for this plot, the major takeaway here is that even the CFD predictions do a pretty poor job in capturing the noise at the beginning, in front and directly behind the blade, right? But we're within 5% of our CFD data. So for our conceptual design work, that seems pretty okay. I'll take that any day. But the biggest takeaway is that this took about 2,250 CPU hours, and this took about 3.83 seconds, right? This took about 650 CPU hours. This took 6.22 seconds. And this is what we need when we talk about how can you integrate some of the medium fidelity models into optimization. You can't run this if you want to do any optimization of aircraft, right? It's impossible. But we can get in the ballpark using the methods that are pretty fast and robust. Now, we have a model. Let's actually apply, and this is coming out the end of my talk. Let's actually apply it to rotorcraft design. Professor Scherer in 1999, you developed this model which captures the essential elements of blade design, right? This is rotor blade design as well as wind tunnel and wind turbine design. And he mentioned the fact that the three important elements are structural design, condition monitoring, and aerodynamic design. This was done in 1999. Well, I argue that this needs to be modified for today, right? Where noise is a significant contributor to, well, not only annoyance, but also it'll be a significant factor in certification. So let's look at blade design, and this is where I'm going to be a little bit more educational for the audience here. Let's look at some of the elements of blade design and how do they impact on the sound. Well, if you decrease blade solidity, which is essentially the thickness of the blade, you can imagine you're reducing the disturbance in the air. When you reduce that disturbance in the air, you're reducing the harmonic component, right? And by decreasing the blade solidity, you can also improve on the performance of the blade. But not all trends follow the same direction. For example, if you increase the number of blades, you're increasing the blade passing frequency. So you're actually increasing the frequency, of the recorded sound. And obviously, if you're increasing the number of blades, you're decreasing the loading of the blade. But that is not necessarily always a good thing. Because if you look at the A weighting scale is the perception scale of essentially applying a human perception to natural sound. You see here that for the old spectrum, the A weighting is able to subtract a pretty good amount. So essentially, it's not going to disturb the human that much compared to this amount here. It shows you that the A weighting doesn't really have an effect on the noise. So what I'm trying to convey here is that you really need to understand all the different elements of blade design to understand how can you design a blade that has low noise. And then lastly, blade twists can also reduce noise by moving the load inboard. When you're moving the load inboard, you're essentially moving the harmonics lower. And if I mentioned before, if you look at the A weighting scale again, you have a more significant, essentially negative difference, right? So those harmonics at those lower frequencies will be essentially reduced more in terms of human annoyance, right? So these are just elements of rotor design, some of them. In my thesis, I have about 10, but essentially these are some of them that you have to consider when you're doing blade design. Looking at a case now, I'm gonna essentially optimize a particular rotor blade. Here you have the aerodynamic constraints, which is the figure of merit, as well as the solid pressure level. And these are just you have the aerodynamic, aeroacoustic constraint, and then alpha is just the optimization weighting between the two. So obviously you can vary essentially if you want to optimize the blade for performance versus noise. And then these are just the optimization variables. Does anyone want to guess why the design load is M2 over M minus 2? And not just N? And this is a common mistake by aircraft designers that, when I speak to a lot of eVTOL designers, they don't do this. The reason is because when you're designing an eVTOL, you want to design for the worst condition. The worst condition is when you have one rotor blade inoperative, and as a result, you need to shut off another rotor blade to balance the aircraft. This is a common mistake made by eVTOL designs, right? So this is just showing you when you design a rotor blades, you really want to design for the worst condition. And then looking at the results, these are some preliminary results, but as you can imagine, when the alpha is close to 0, when you're really paying attention to the acoustic signature, the performance, the power of the blade is pretty high compared to if you're looking only at the performance, alpha equals 1, the power consumption of the blade is obviously lower, but the noise is pretty high. And we expect there should be like a Pareto frontier in that area there. And this is what we see in the results, right? For blade designs with low noise, we see essentially thicker chords, and you have essentially a less pronounced angle of attack. But what does this really mean, though? Well, if you look at aircraft in existence today. If you look at all of them, what do you see? You see high solidity, right? They're paying attention to noise. And so these are some of the preliminary results I'm showing you here, just convey some of the things you're seeing in the in presence today. And then looking at the acoustic footprint of this aircraft, let's compare the baseline aircraft to an alpha of 0.5. So we're essentially weighting the performance and noise the same. We see there's significant reduction in noise within the, this plot here is essentially just this flight profile. So we see that there's significant reduction in noise when the aircraft is reaching its descent phase. And that's what we want, right? If you have schools and buildings around here, we want to reduce the noise footprint of the aircraft, right? That's something that we're interested in. And then to tie it off, I think this is the last technical slide, but to tie it off, these are just the results when you compare the performance, right? The blue line is just the Atkins and Liebeck method for propeller design. Obviously, it's not suitable for rotor design, but you can see here, when you increase, when we consider noise, we see obviously there's a reduction in sound pressure level, but we obviously see the increases in power and energy consumption. And these are important plots for systems designers, right? Where you want to make trade-offs between the two, right? This is very critical for not only systems designers, but also for consumers and the general public. So the future work is as following. We want to first do some flight trajectory optimization. Now we have a model for predicting aircraft performance. Can we optimize the flight trajectory not only for noise, but also for battery cell degradation, right? And that's taking in those temporal effects. And then can we also do urban canyon and digital elevation noise? Essentially, can we model the noise over any given elevation? And then last but not least, exploring in multidisciplinary coupling between the two, using higher fidelity, medium to higher fidelity methods. So that's something that we want to do. And then my concluding remarks is the following, just two simple ones. The first, that the integration of these medium fidelity techniques can really inform critical choices. And here's the important part, early in the design process, right? The early choices you make in design have a significant impact on the revenue of the aircraft, a significant impact on future modifications of the aircraft. And then lastly, and this is very critical to any research endeavor or any scientist or professor out there, can these computational approaches be used for other applications, right? So for noise, obviously prop fan aircraft, and then for batteries, this modeling can be used for PEVs, right? Personal electric vehicles. And I want to close with this slide because it really just captures some of the things I believe are going to be impacting impacting urban air mobility. It just summarizes my entire talk. The first is essentially on acoustics. And then the last is on these two guys here. And if you want, after you can come and see them, but these are just batteries for lithium-ion aircraft. And I think these are the two biggest issues that are facing aircraft, the realization of urban air mobility systems today. And then lastly, after some time, once we have that understood, then looking at scoping the future of regional and urban air mobility to really realize this idea. So with that, I want to thank everyone here and open for questions.
So who's close to deploying some of these aircraft? A lot of people, a lot of companies that seem to be developing. Are we going to see some of these flying around here?
There are a few companies that are really close. Joby obviously is the first one that comes to mind. Archer, it's pretty good. Vertical, I've heard some good things about Vertical. So those are the three that I would say within the United States that have a viable, not only an aircraft that is an aircraft that can do a lot of different missions, right? I think that's the if you want to sell your product to a customer, you need to sell all of the missions that I showed you before. But there are a few within the next few years.
So are they in the certification process right now? Has that started?
They're in the certification process right now. And actually, I think one of these slides here actually tells you, if it can go to it. This is the issue they're having. I think I spoke with Professor Frew about this earlier. The fact that the problem with certification right now is that for cars, there's something called UDOS, which is essentially like a drive cycle system that there's a lot of certification on. There's nothing for aircraft, right? So like we need to actually come up with a particular characteristic power profile that we can use to certify electric aircraft. And not only that, what electric aircraft are suited for this type of characteristic profile. We don't expect this profile to be used for all types of eVTOLs. So to answer your question short, the problem right now is the fact that there's not already a lot of certification. There's a lot of certification work, but it's not really, I think a better job can be done with direction.
So going back to the aeroacoustic noise work, the optimization problem, sort of have two questions related to that. One is, what role does, say, prop phasing? So, for example, the eVTOL concept that you showed has like 10 props. And so thinking about in terms of harmonic noise production, specifically the radial directions, can you, say, potentially redistribute or get active?
Yeah.
You know what I mean? So harmonic interactions with baby. That's one question. And then
I'm just drawing a plot here to show you what the effect of harmonic phasing would do. It essentially makes these peaks, spreads out the energy.
exactly.
Yeah.
Yeah, so you could actually run all of the props at different
Phases,
angles,
yeah.
And then as you get further away in the radiated sense,
Yeah.
Now you've removed the primary harmonics, you just did broadband.
Yes.
Does that have a benefit for perception?
It does, because it depends on where. It depends on where you distribute the noise to on the A weighting scale, right? But generally speaking, if you distribute the energy, it does. The issues with that is when you have phasing, from a dynamical point, you have to account for the different torques of the different rotors. So these are the small nuances. Yeah. These are the small nuances that a lot of eVTOL companies, when they come to us, they're facing. You have these simple models for motor torque, but just technically torque in 3 different axes, etc. There's a lot of things that go on in terms of modeling the dynamic loads.
But I guess that's the question: is could you actually rework your tool, or is it possible, even as it exists now, to optimize the phasing, or say receive noise instead of say optimize the color design?
Yeah, you remember that phi of s that I talked about in that equation? Changing that phi of s, essentially you're changing the phase, right? So you can essentially just add the 2 together.
And then kind of related to that is the same idea as thinking not of a single propeller, but thinking of the system. And so redistributing, say, the loads and having, say, different propellers. If you have this eVTOL with 10 props, maybe you have different props at different span locations, and that kind of get sort of different constructive and destructive interferences.
Yeah. Exactly. For that, I think that's definitely where high fidelity tools come into play, because the amount of, you not only have to look at your loading, but the wakes of those aircraft create a significant, contribute a lot of noise too. So that's where, in my postdoc, one of the things I want to do is to spend more time doing high fidelity modeling and then doing some multi-fidelity optimization. I think that's where and I think Ken, we spoke about this last time. That's where my research direction is probably going to go.
On the battery model, so it seems like this investigation is looking at point between, and so kind of looking at forecasting energy storage development is sort of happening currently. Should new technologies come into play, how much of the versus, you know, how difficult it is in the event of an eVTOL.
Yeah.
Game changers,
Good question. Using empirical-based models obviously limits that, and that is why I think moving towards 2D particle transfer models, where you're modeling the transfer of particles within a battery, is better, because once you do that, once you have if you know how the batteries are going to be improving every year, you can essentially change the properties of those mathematical models to essentially inform, to give a more recent estimate of the performance. Supercapacitors, I think the military has talked about using supercapacitors. I haven't modeled that work here, but I'm sure there are similar equations, first order up the way to higher fidelity methods to model this. So like I mentioned before, one of the things I want to do in my postdoctoral work is to moving away from empirical models and going towards models that are more physics-based, right? I think that's the only way you can, if someone calls you tomorrow from Sila Technologies or Tesla and say, hey, we're going to change the concentration of the cathode, can you model it? That's the only way to do it, right? So I think that's where I want to take my research.
Questions?